This is for four derivatives of exponential and logarithmic functions. The derivative, this is a favorite derivative here, d dx of e to the x is itself e to the x. Of course, you got to use the chain rule if x is anything besides just x. So if you have a function, a composition of functions there, you got to remember to use the chain rule. So you'd have to multiply by the derivative of whatever the power is. This is derived using the definition of derivative. It's just f of x plus h minus f of x over h, and a little identity there that we've talked about in the beginning. It's a little bit of algebraic magic, and you can derive that one. But that's the e to the x derivative. The derivative of a to the x is equal to a to the x, and you got to attach an ln of a. And what we end up doing with that one is taking e to the x. You can actually take e to the x and rewrite it as e. Let's see. Yeah. So you can write it as a to the x is the same as e to the x ln of a. Remember that we can move the x out over here, and so the e to the power of ln undo each other, leaving you with just a to the x. So we write it as e to the x ln of a, and then take the derivative of e to the x ln of a and use the chain rule on it, and you come up with a to the x ln of a. So similarities, you copy down the function. Difference is any other base besides e, you've got to attach an ln of the base to it. All right, the other two, d dx of ln of x is equal to 1 over x, and d dx of log any other base besides e of x is equal to 1 over x, and then attach an ln of that base. So don't forget to use a chain rule on these when x isn't just x. So really think about similarities and differences on these, but these are the last four of the derivative rules. And so we should have now the skills to do that worksheet 4.2 that puts all this together. We got our trig derivatives, both the inverses and the original. We've got chain rule on there, and now these four new derivatives. So there they are. We're going to look at some examples. They all involve chain rule along with these four. So here we go. First one, example 1, is d dx of e to the negative x over 4. The way to think about this one is, well, first of all, just copy down what you have. So we have e to the, and it might help too to think of this as negative 1/4 x, if you will. But we just copy down what you have there, and then it's times d dx of e to the negative 1/4 x power. And that's equal to e to the negative x over 4 times negative 1/4. And you can throw that negative 1/4 out in front, which is typically what they'll do. So it'll look like this. Negative 1/4 e to the negative x over 4 is probably the cleanest way to write that. So there's our e to a power derivative. The next one, we've got some other base besides e. Thinking about similarities here from our e to the x derivative is we copy down the exponential expression there just as you see it. So we've got 3 to the cotangent x, and then we've got to attach, sorry, this is one of the differences between e to a power and some other base to a power, is attach ln of the base to it, so multiply by ln of 3. And then we've still got to do d dx of the power cotangent of x. And then we've got 3 to the power of cotangent of x, ln of 3, and then the derivative of cotangent is negative cosecant squared of x. And that's it. All right, we'll look at the other two here. We have d dx of ln of x squared plus 1. So first thing we do is write 1 over the argument, so 1 over x squared plus 1, and then it's times d dx of just the argument, x squared plus 1. And derivative of x squared plus 1 is 2x. We'll place that over the top of the x squared plus 1, and we've got it. And the final one, think about similarities here. It's similar to the one above in that we're going to take 1 over square root of x plus 1 to start. But then we have to attach as a product on the bottom ln of the base of that logarithm. It's something other than e. So we have an ln of 10 down there times d dx. And we're going to think of this as x plus 1 to the 1/2 power. So we've got 1 over square root x plus 1 ln of 10 times 1/2 x plus 1 to the negative 1/2. And this one actually simplifies pretty nicely. Let me show you here. You can move the, this thing right here. I'm going to get rid of this. The ln of 10 is not underneath the radical. So we've got 1 over, there's a 2 here, ln of 10. So that 2 comes down to the bottom. And then this right here can be rewritten as the square root of x plus 1 in the bottom. Well, you have a square root of x plus 1, and then you put in another square root of x plus 1. And you've got 1 over 2 ln of 10 times x plus 1. The radicals undo each other. So remember, 2 ln of 10 is just a constant, it's a number. So you have that constant times x plus 1 on the bottom. So there they are, the 4 of them with chain rule involved as well. Right, one other thing to point out here is one other technique here is this is an algebraic rewrite of something. And we bring this up in this section because it looks kind of like the derivatives we just did. But notice this right here is a variable. It is not e, nor is it a number like 3, like in my second example. It is a variable. So we have a variable to a power. So you cannot apply the derivative rules we just learned to this one. There is a way to handle this. It's called logarithmic differentiation. The step process is up there. Step 1 is to take the log of each side of the equation. So we're going to take the log of each side of the equation. So we'll do that first. It looks like this. We're going to take log base e. So ln of y equals ln of x to the tangent x power. So that's the first step. So step number 1, write that step down and do it. Let's take the log of each side of the equation. Now the reason we take the log of each side of the equation is so that we can rewrite this right-hand side. We can take and write tangent of x times ln of x by the rules of logarithms. And that equals ln of y. Now we're all set up to differentiate implicitly, and that'll be our second step. On the left, we've got ln of y. We are going to differentiate this. It's 1 over y, but then I've got to attach a dy dx to it. So ultimately, we're going to get our derivative in terms of x. So we're treating y like it's a function in x. And then on the right side, we've got the product rule. The derivative of the first is secant squared x times the second. And then we've got plus the derivative of the second, which is 1 over x times the first tangent of x. So that's the second step, is differentiate implicitly. We're going to go ahead and solve this for dy dx by multiplying each side by y. So dy dx equals y times all of this. And then the final step is taking what y is equal to up here in the top and use substitution to get our derivative all in terms of x. So I can replace y with x tangent x. So dy dx equals x tangent x times secant squared x ln of x plus, you can write this as tangent x over x. That's our final solution. So that's using logarithmic differentiation. So do not confuse those. When you have a variable base to a variable power, it's not the same as a numerical base to a variable power. So you can't use the new rules for e to the x or a to the x to find the derivative. But you can bring that power down using logs of each side. One other thing, just to point out here, is you don't use today's rules to derive this guy, because once again, this is a variable power. But because this is a constant, and it is a real number, it's irrational but real, we can rewrite this as y prime equals, using the power rule, pi x to the, and we would just express this as pi minus 1 because of that irrational number in there. Just take the irrational number, stop on a minus 1, and we can apply the power rule to that. So you could throw in like that in on you. So hopefully this is helpful. Go ahead and try the homework from the textbook.